The third model we're going to look at modeling data is using the logistic function. And we're going to use a logistic function whenever we have certain requirements or criteria that would allow us to think that this would be an appropriate model. And this is what they describe at the beginning. The exponential logarithmic models, they are unlimited. They increase without restriction. And that's typically not the way most growth problems occur in nature, because we always have some type of limiting factors. And they say in many growth situations, the amount of growth is limited by factors that sustain the population, such as space, food, and water. So when we're looking at population growth, either bacteria or animals or fish or humans, whatever the case might be, we do have this restriction that applies, and we just can't have unlimited growth. It can't keep increasing forever and ever and ever. If that's the case, and you suspect that from the context of the problem, then a better model that you could pick is called logistic growth function. And this model is one that has a resource-limited exponential growth. And you've got the key concept here, logistic growth function, and you can see that the pattern of the graph is it increases exponentially at first, and it levels off, and it hits a ceiling or a limit. There's a physical limit to where we can't go beyond because our physical constraints will not allow it. So that's what the kind of growth problem that we're going to be working with. And they've got a little study tip over here. They say if the b in this function is negative or less than 0, then we actually have a logistic decay. And they say dismiss that idea for a little bit, because we're only going to work with logistic growth so far in what we're going to be studying. So logistic growth functions are bounded by two horizontal asymptotes at y equals 0, so we cannot cross the x-axis. We can't go below a certain population, can't go below extinction. Once you're extinct, that's as low as you can go. And then we also have this physical constraint where what is the ceiling, the upper limit of what your population growth can be. So that's the first thing we're going to do. I'm going to take a little time out so I don't use the time on the video to enter the data, and then I'll come back after I have the data entered in the calculator and pick this topic back. Okay, it took a little time and I recorded the data in the list 1, list 2 of the calculator. What we have here is a population of fish, and it's limited by the space and the size and the food sources that they have in the pond or the lake. So in list 1 I put the years in months, I'm sorry, the time in months, anywhere from 0 to 24. So this is a 2-year period of calculating the fish population, and in list 2 is the population of the fish. So they tell us very specifically to use a logistic regression, which in the context of the problem, or a logistic regression sounds like the type that we should use based on the description they gave us on that. There's not unlimited growth in a fish population in a limited size space of the lake. So what we do is we go to our stat, we're going to calculate, and we're going to go down, we're going to pick the appropriate regression, which we're looking for a logistic. There's our logistic regression. We hit enter, and it's going to be list 1, list 2. We're going to store this in, just as we have been, in the y bars, which is the function, and I'm going to place it back in y1. I'm going to hit the calculate button, and we're going to calculate a logistic regression. Now on these, I do not believe that they're going to give us a correlation coefficient, and they do not. So with this, we won't get that model where we get the correlation coefficient, but I want to record these numbers before I go too far away from that, so I'll have to kind of go back and forth on the screen here a little bit to get these recorded. So rather than writing the whole complicated equation here to start off with, I'm just going to first try to record the data. So let's just go 64.7 since we've rounded to the hundredths, and that's not going to be too difficult to do. So again, go back and get B. B is 0.39, so 0.39. And we also need C, and the value of C is 8,498.86. 8,498.86. I'm coming back and just making sure I got those numbers recorded. Just a second check there. Okay, so you can see that the form of the equation, they even give you the form of the equation up here in your calculator. This is what we have to put A, B, and C in. I'm going to come back and put that in a little bit later and get the whole equation. They really don't ask us to write that model out, but we're going to write the model out in the algebraic equation. And now what we want to do is answer the question that says, use your model to predict the limit to the growth of the fish population. So one of the things I want to make sure I do is I want to get an appropriate window. Right now we're going to 24 months, so we're going to go 0 to, what if I double it, went to 48 months, and I can always change that to and go higher and higher months. We can go up to 60 months to get 5 years growth. And maybe that's probably more appropriate. I'm going to get up to 60 months, which represent 5 years worth of growth in this fish population. We'll go by tens. The Y-min, the population started at 125, so I'm going to go ahead and zero that out, start at 0. It's got to go up to a population of 8450. We're assuming it's going to grow beyond that, so I'm going to go up to, I'm going to hit 15,000 just as a starter. Maybe it's wrong. If that's the case, then I'm just going to have to make some adjustments on that. And then I would probably want to go by 1000s for scales. So I can graph the two things. The first thing should be our scatter plot. The next thing is going to be our regression equation, which looks like we're seeing a pretty good fit. So now, how do we use this to estimate our population growth? Well, one of the things I might look at, since it might be a little bit hard to figure out where this is flatlining, maybe you can go to your table. We haven't used tables for a while, but I'm going to go to table set. I'm going to start this at, and what we're looking at are the X values. We're going to go from month, we can go from month 24, that would be where we want to go, and we're going to go by 1 month intervals. And I'm going to go back to my table, and I'm going to see what these values seem to be approaching, hopefully, if I can get this to click on it. Okay, so I'm going to look at my Y1 to see the population, and is there something where the population is seeming to be leveling off? And it looks like it's leveling off with that 8,498.8, and there's very little change in there. So maybe 8,498. We might get to 8,499 eventually, but you can see it's barely moving. I'm going out many years out there. So it looks like it's going to limit itself right out here at 8,498.9, or if you want to be a little bit more practical, how about 8,499? So 8,499 appears to be the ceiling or the limit on that population that lake can sustain. Now, last thing I want to do is probably rewrite the equation. So since we have all the parameters here, we're going to go fit that back in our logistical model back here. So we want the number of fish after amount of time is equal to, our constant was 8,499 for C, and it's going to be 1 plus A. We had a value of 64.7. We've got to take that times E raised to the negative value of B, which is 0.39, times T. And that's the equation that should model this growth, logistic growth fairly well.